Yeah, good day everyone. I trust everyone is keeping well. Welcome to the first episode of the channel. Today we are dealing with patterns, sequence, and series. So today's topic is a 3 weeks topic and it weighs about 25 marks plus minus. So it's around 25 to 22 marks, between 25 and 22 marks on your paper 1 mathematics grade 12. So stay tuned and I hope everyone enjoys the topic for the day. So today's topic is patterns, sequences, and series. So on today's topic we will be looking into the number patterns, including the arithmetic and geometric sequences and series. We will then deal with sigma notation, and then lastly we will be looking into the derivation and application of the formulae for the sum of arithmetic and geometric sequence series. So on today's topic we will be splitting in the lesson into 3 parts. So the first part, it's purely arithmetic and geometric sequences and series, and then on the second lesson we will be introducing the Greek symbol and the meaning, and then lastly we will be of course looking into the formulae for the sum of the arithmetic and geometric series. So the objectives of lesson 1, the learners or the audience will formulate an equation to represent the types of sequences. Then we will be looking into the summation to represent an arithmetic series, and then obviously the learners will later be introduced on ways and methods on how to calculate the sum of the series. So there are 3 types of sequences in this topic. We will only be dealing with 3. That is the arithmetic, also known as the linear pattern. We will also be looking into a quadratic sequence. Then lastly we will be looking into a geometric, also known as an exponential sequence or an exponential progression. So an arithmetic sequence, by definition, all first differences are equal. That is, you always add or subtract a constant difference. So if you have a look onto an image shown on your right, we have 2 types of arithmetic sequences. One would be presented by an increasing pattern. By increasing I mean your difference is always positive. Your first difference is constant and will be always positive, meaning your first term will always be smaller than the subsequent terms. And then the decreasing arithmetic sequence, you will notice it by a negative common difference, meaning your first term will always be larger than the subsequent terms. So what do we mean by a common difference? A common difference is calculated by finding a difference between the immediate next terms. So that difference should be a constant, so hence it's common. So the general term for an arithmetic sequence is expressed by an equation as stated above, where A is the first term of the sequence, D, like explained, it's a common difference and it's the first common difference. You will understand why I put an emphasis into the word first. And then your N in the expression is the rank or the term position. T1, T2, T3, T4, and so forth. And then Tn is the term number, meaning it's the value of the ranking, the value that will appear on the ranking. If I use an example, if you look at an increasing arithmetic sequence, our A would then be number 5, because 5 is the first term on the sequence, and then D would be 4, because if you subtract the difference between the subsequent terms, you get a constant value of 4. And then the rank or the position, if we look at term number 13, term number 13 would be having a rank of 3, because it's the third term in the sequence. So that is basically our arithmetic sequence, and it's all you need to know about the arithmetic sequence. And then our second sequence is known as a quadratic sequence. A quadratic sequence is when you find the second difference, you find that your second difference are equal, where the first term form an arithmetic sequence. And what do we mean by that? If we look at our picture on the right, the sequence is 4, 7, 12, 9, and 28. And then if you have a look in our first difference, if we subtract the difference between the subsequent terms, if you take 4 away from 7, you get 3. You take 7 away from 12, you get 5, and so on. So if you notice here, the first difference gives us an arithmetic sequence, because then if you get the difference in the first difference, you get a constant. So this now is what is explained in the definition of a quadratic sequence. So your second difference is a constant. You get a common difference when you get the second difference, whereby your first difference is an arithmetic sequence. So the general term is expressed by the statement as stated on the equation that is highlighted by our pointer. And then obviously you have your A, your B, and the C. So to calculate the values of A, B, and C, you use the following equations. 2A is equals to your second difference, which is a constant. In this case is 2. 3A plus B is equals to the first difference. So 3A plus B would be equals to the first term in the first difference. So in this case it would be 3. And then A plus B plus C is equals to term 1. So A plus B plus C in this regard would be term 1, which is 4. So if we were to go on and calculate for the values of A, B, and C, in this case we would say 2A is equals to number 2, therefore A would be 1, and then 3A plus B is equals to the first difference. The first difference is term number 3. So in this case we would say 3A plus B is equals to 3, because 3 is the first term in the first difference. Solving for B in this regard, we would then substitute A, that was calculated as 1, and then B would be 0. And then if we had to go on and get the other constant, that is now C, we would substitute A and B, then try and solve for C. A plus B plus C is equals to term 1 on the sequence, that is 4. If we substitute A being 1, B being 0, we can simply solve for C, and C in this regard would be 3. I understand I'm not showing these calculations. I just want the audience to try and work this problem themselves. This quadratic sequence was dealt with in the grade 11, so we are also bringing it in this lesson today because it can be examined during the final exams. The general term of this sequence would be n squared plus 3. Let's test if n squared plus 3 would work. Let's try testing by finding the fourth term, t4. So if we were to find t4, we would substitute 4 into n squared plus 3. 4 squared plus 3 would be 16 plus 3, which is 19, meaning that our n squared plus 3 is a general expression for the sequence as shown on the picture. But otherwise, no worries for now, because during our next episode we will be looking into the past exam question papers, where we will be using selected past papers to cover the topic. So we will use examples from the past papers to try and represent how one would go about solving problems of this topic. Then our last sequence on this topic is a geometric sequence. A geometric sequence by definition is expressed by a constant ratio, that is, you multiply by the same ratio. So if you look on the picture as shown, our sequence is 1, 4, 16, 64. Clearly you can see from the first term we multiplied 4 to get the second term. Second term we multiplied by 4 to get the third term, and so on. So if you reverse the sequence, you would then divide. Hence, that's why we see a division of 4 from right going to left. So if you see that our common ratio, as you can see, our common ratio is 4, meaning you divide the subsequent terms. So t3 divided by t2 is 4. 16 divided by 4 is 4, which is also equals to t2 divided by t1. So 4 divided by 1 is clearly 4. So the ratio is a constant. We have a common ratio. So the general term for the geometric sequence is expressed by ar to the power n minus 1. This is the general term for a geometric sequence, and a is still the same. It's the first term of the sequence. R is the common ratio, n is still the rank or the position of the term, and Tn is the term number, the value on the sequence. So now we are looking into the sums of series, the nth terms. So for an arithmetic sequence, we get this expression to calculate the sum of the series. So you can calculate for any sum of the series expressed by a sequence using this expression here. This expression can also be presented by Sn equals to n over 2 multiplied by a plus l, where l is the last term or the nth term. So later on we will be looking into the derivation of these expressions to get the sum of the series on an arithmetic sequence as well as a geometric sequence. So on your right we see a geometric sequence and the expression of the sum of the series on a geometric sequence. So obviously there is a restriction here for this equation. We are saying r cannot be equals to 1, because if you see we have a division here of r minus 1. If r is equals to 1, the expression would be undefined, hence this expression applies. So also there is a sum to infinity, which is expressed by this expression is shown on the pointer. And then we must have a note as well that the terms for convergence are any values of r that are less than 1 but greater than a -1. We will also try to show what we mean by that graphically during our next episode as well. Okay, everyone. Now we are quickly gonna be moving to lesson number 2, where we will be dealing with a sigma notation. The sigma notation is basically a representation of the terms of a series, and each term is usually associated with a letter and the corresponding index. So the lower and the upper bounds of the sigma notation indicate the starting and ending values of the index variable. So in this case, the index variable would be n, as shown on the picture is the index of the summation, and then the lower bound is n equals to 1, meaning this is the starting point of our sequence, and then the last value of n would be our upper bound. And then the formula for the term is usually placed on the right hand side. So sigma is this notation here, and it means sum from this lower bound to the upper bound. We'll see what we mean by that as we go on. So sigma is a Greek capital letter, and it indicates the summation and is used as a shorthand notation for the sum of terms that follow a pattern. So this is just a short representation of the sum of terms. That's why we use sigma. By using sigma, we are showing that we are actually doing a summation of the terms in a sequence. So lesson 2, as I said, it's a sigma notation. So the objectives of covering this topic, we will later want to represent and demonstrate how to expand sequences from a sigma notation. Also, we will be expressing and evaluating the sums using the same notation, sigma notation. So sigma notation, I tried to come up with 3 different examples where we will be showing how to expand a sequence from a sigma notation. Then we will also be showing how to express the sums using the sigma notation, and lastly we will be demonstrating how to evaluate the sums using the same notation, sigma notation. So expanding here means you have a sigma notation, so they have a general term here. They are saying find the sum of the terms on the sequence starting from term 1 ending at term 5 using this expression. So all we do here, we substitute the starting point to this expression as shown 1. We start from 1, then we end at 5. As it is demonstrated here on the notation, we start at 1, we end at 5. So we start from 1, we go to the next one, the next term, until 5, and then we express or expand. We expand the values generated from this expression, and then we get our number 55. So the expression is n squared. So we'll obviously start by substituting n equals to 1 into n squared, we get 1. N equals to 2 into n squared, we get 4, and so on. So if you evaluate this, if you expand this, you will get 55. So if the question in the exam asks us to expand without using a calculator, you will be expected to show all the steps without finding the final answer by punching in the sigma notation on your calculator. But it's always a good practice to also check the expression in case you may have made any mistakes there. So expressing the sums using sigma notation, we have an exemplary sum here, 1 over 5 plus 1 over 7 and so on. So if we were to show this sum using the sigma notation, we would first want to find the general term of the sum. As you have seen here, my immediate next step, I noticed that we actually have an arithmetic sequence on the denominator, so I made everything to be all over 1, as you see here. So I recognized an arithmetic pattern or an arithmetic progression, hence I applied the general formula for the arithmetic sequence here. So my first term is 5. As you see, I substituted 5, and the common difference here is 2. I substituted 2 here. So if you expand or evaluate this, you get 2n plus 3. So 1 over tn was my final. 1 over tn was 1 over 2n plus 3, as shown here. So if we had to take this and express it using sigma notation, we get an expression like this. So our n equals to 1 would obviously be the first term, and we end at 4. Term number 4. There is only 4 terms in this expression, so that's why our upper bound was 4 and then the lower bound was 1. So if we test this by substituting the lower bound, n equals to 1, we obviously get 1 over 2 times 1 plus 3, which is 1 over 5. So this is an expression of sums using sigma notation for the exemplary sequence as shown. So lastly, we are going to be looking into evaluating sums using sigma notation. So here I didn't want to confuse the audience too much, so I used the two expressions as we dealt with here. So for an example, if we had to evaluate the sums of 1 over 2n plus 3 plus the sum of n squared, we would obviously be taking the sum of n squared starting from 1 to 4 as 55 as calculated here, and then we would be taking the sum of this expression 1 over 2n plus 3 starting from 1 to 4 as 1 over 32, because I basically added all these expressions here, and then we ended at 1 over 32. So summing up these two values, we get approximately about 55.03. So basically this is how you would evaluate the sums of sequence using sigma notation. Otherwise, we will also be looking further into sigma notations when we're dealing with the exemplary questions from the chosen past papers, and that's coming up on our next episode. So the last lesson of the topic, we are now going to be looking into the derivation and application of the formulae. The first one would be arithmetic or a linear progression. Then lastly, we will be looking into deriving a geometric progression. It's also known as an exponential progression. So the general expression for an arithmetic series would be expressed by the top statement as shown. the sum of n terms is equals to a being the first value, plus the second value would be a plus the difference, common difference. That value would be a plus 2d, and so on. So the trick here is that you create the second expression by rearranging your sequence, meaning you take your last term, you write them first, you write your sequence in reverse basically, then you add the two statements as shown. So immediately you will see that if you add your first statement and the second statement together, you will end up getting a plus l for all. You will be getting a plus l for all, and then if you sum the left hand side together as well, you will be having 2sn. So noting that there are still n terms on the right hand side, we will add n to represent the number of terms which are on the right hand side. So you will end up with an expression like this. So basically you now want to express the sum of the sequence. You will just express the sum of the sequence. You'll make it the subject of the formula, so you will divide both sides by 2, then you will have the expression as shown on your right hand side. So as stated previously, that our L denotes the last term of the sequence, and the last term of the sequence is also expressed by a plus n minus 1 multiplied by your common difference. So if you substitute L into this expression, you get that, and then that's how you basically derive your arithmetic sum. I hope it makes sense. Okay, ladies and gentlemen, now we will be showing a derivation of a geometric sum. So the general expression for a geometric series would be a plus ar plus ar squared plus ar cubed, and so on and so on, whereas your last term would be expressed by ar to the power n minus 1. So this is the general statement for the general expression of your geometric sequence. So if you look into the general expression and multiplying both sides by the common ratio r, you will get on your left hand side r multiplied by Sn, then you get that, then you multiply each and every term on the sequence or the series by the common ratio, then we end up getting that. So subtracting the two statements above, we will get on the left hand side Sn minus rsn, and then on the right hand side we will get a minus ar to the power n. The other terms would be subtracting each other in between basically. And then if we take out the common factors both on the left and right, the common factor on the right would be, on the left would be Sn, then would be left with 1 minus r. On the right, the common factor will be a, then would be left with 1 minus r to the power n. And then if we express Sn as the subject of the formula, we then end up getting this statement or expression as shown here. Obviously there is an applicable restriction to the formulae. We can't divide anything by 0, since that would give an undefined value. Okay, the applications of the formulae for arithmetic sequences, we would apply it in real life problems such as stacking cups, chairs, bowls, and so on. and then we would apply it in the fencing and parameters and stuff like that. And then the geometric sequences, we would usually apply it calculating the compound interest, calculating the population growth of the country, or so on. Some use it in electric circuits, and then financial mathematics, we get the present values and so on. So today's lesson, guys, we covered the number patterns, which we now know that there are sequences of numbers that follow a particular rule, and this rule, Tn, is the nth term of the sequence or number pattern in terms of the term number n. Arithmetic series and geometric series are sums of the terms of an arithmetic sequence and the geometric sequence respectively. Sigma notation is a very useful notation for the sum of a given number of terms of a sequence. So sigma is a symbol used for sum of. So in real life, the application of the formulae are population growth, compound interest, fencing, and so on. So guys, as previously explained during the presentation, the next episode we will be looking into question 2 and 3 of these two selected past exam papers. The exam written in November 2019 and the final exam written in November 2022. So do not miss the next episode, ladies and gentlemen, and I hope you find it fruitful. Thank you for tuning in. I hope I'll be seeing you guys during the next episode, where we will be mainly dealing with the problems from those two selected question papers. I would appreciate your comment, guys, and any specific questions that you may have. You can comment on the YouTube channel, or you can send a direct email as shown here. You can use that email address to connect to me or reach out to me. Thanks again, everyone. I hope you enjoyed. Bye bye.